Welcome to the video lecture on force due to liquid pressure. Now, force due to liquid pressure requires talking about pressure, so let's define pressure as force per unit area. So pressure P is force divided by area. Fluid pressure is the pressure on an object at depth h in a liquid, and it's given by P equals W times H, where W is the weight density of the liquid per unit volume. So this pressure is dependent on the weight density of the liquid times the depth at which this object is at. Now, some common weight densities that you'll use are for water 62.4 pounds per cubic foot, and in seawater 64.0 pounds per cubic foot. Now we have something called Pascal's principle, which says that the pressure exerted by a fluid at a depth h is transmitted equally in all directions. So for these three different pictures right here, the pressure is going to be the same for all three objects at a depth of h. Now when we talk about fluid force, which is what we're going to be calculating throughout this lecture today, the fluid force on a submerged horizontal surface of area A is given by the pressure times the area. And we know from up above that pressure is defined to be that weight density W times the depth H. So this pressure is W times H times our area A, and so this formula for fluid force just becomes WHA. Now this is when we have a object submerged horizontally. So for example, suppose that a metal sheet is submerged horizontally in 5 feet of water. So imagine having this horizontal sheet laying flat, and it's submerged in 5 feet of water, so this is 5 feet down, and the area of this sheet is 18 square feet. Calculate the fluid force on this metal. Well, first of all, we're talking about water, so the weight density for water is 62.4 pounds per cubic foot, and as we just defined, the fluid force is going to be the pressure, which is this weight density times the depth, times area. So it's pressure times area. And our weight density is this 62.4. The depth that this sheet of metal is at is 5 feet. It's 5 feet submerged in water. And the area of this sheet is that 18 square feet. So we get 62.4 pounds per cubic foot times 5 feet times 18 feet squared. All the feet cancel out, and this is going to be 5,616 pounds of force, fluid force. And this is independent of the size of the body of water that this sheet is in. I mean, it could be in a bathtub, it could be in a pool, it could be in a lake, and that doesn't matter. Now this sheet was submerged horizontally, so that makes finding this fluid force easier. So what we're going to talk about next is what if your surface is submerged vertically? Then the fluid force is going to vary because the depth of this object varies. So imagine that you have this vertically placed object, rectangle in this case, submerged vertically, so it's up and down. Then the depth varies as you go down deeper. There's going to be more pressure down here at the bottom than there will be up here at the top. So we're going to have to use some calculus because this fluid force is varying. So what we're going to do is we're going to take a cross-sectional slice, and I'm going to let the width of that slice be my delta y, and I'm going to let the length of that slice be L of y sub I, and I'm going to let the depth of that slice be h of y sub I. So when we talk about the fluid force on just that little slice, so the amount of fluid force on just that little slice at that eighth slice, if you will, it's going to be that weight density W times the depth, which is this h of y sub I. So this is that W times that depth times our area. Now what would be the area of this? Well, this little slice is in the shape of a rectangle, so we need its length, which is our L of y sub I times its thickness, which is our delta y. So this is the amount of fluid force in just that slice. If we add up all these slices and let these thicknesses delta y go to 0 in a limit, then this is going to turn into an integral, and it gives us our formula for fluid force, which is going to be the integral of, I'm going to pull that weight density since it's a constant out front, from C to D of our height function h of y times our length function L of y dy. And notice the bounds here are y bounds from C up to D along that y-axis. And this is called fluid force. Okay, so this is going to be the formula that we're using for all of our problems. The weight density times the integral of the height times the length dy. Now when we're doing these, one word of advice is to always measure the depth from the top down. So in this first example, we want to find the fluid force on the indicated vertical side of a tank. Assume the tank is full of water. So this is what I'm going to have my tank look like. It's just going to be a 5x4 rectangle, just like this. And what I want to do here for all of these problems is it's important to set up a coordinate system. So if this is my tank, what I want to do is place it on a set of axes so that I can make sure that I'm using the right depth function and length function. Now, most of the time for these problems, what I usually end up doing is trying to center this or sort of position it near that origin. So what I'm going to do is I'm going to let my y-axis come down like this, and my x-axis is going to be along the top up here. And there's my coordinate system. And what I'm going to do is I'm going to draw in a little slice, a little horizontal slice, which has a thickness of delta y. And I would recommend labeling the top of your tank and the side point of your little slice here, because that vertical distance right there from here to here is going to be our h. And in order to figure out a function for that h, let's label our points. Now these are 2 points that are both vertical, so they share the same x value. The top point is on the x-axis by the way that I positioned it, so its y value would be 0. And this point over here, I'm just going to let be some random x comma y value. So its y coordinate would just be some y value. Now our height function, our depth function if you will, is going to be the length here. And what we're going to want to do is make sure we use direction appropriately. So we want to take the top point, the top y value, minus the bottom y value. So we're going to do 0 minus y, so that this depth is actually going to be negative y. And in a lot of these problems, your height function, your h of y, will be negative because you're going from the top down. Now for my length function, I need to figure out how wide this is, and because this is just a nice rectangle, no matter where I draw that slice, how wide is it going to be? Well, it's always going to be 4 units wide because, or excuse me, 5 units wide because of my rectangle having a width of 5. So my length here is constant of 5. So our fluid force formula is this weight density times the integral of our height, or depth if you will, times the length times dy. So we now know all of these pieces. We're talking about water, so the weight density of water is 62.4 pounds per cubic foot. Our depth function was this negative y. Our length was always 5. And we have our dy, and now we just need to figure out our units here, or excuse me, our bounds here for y. If y is starting at the top, then that's going to be 0, right? And I want to go all the way down to the bottom of my rectangle, which would be on my coordinate system at a height of negative 4. So I need to go from negative 4 up to 0. So my bounds are going to be negative 4 up to 0. So that's the integral that I want to solve. So if I go ahead and integrate this, I'm going to get that 62.4 times the integral of negative 5y dy, which is just 62.4 times negative 5 y squared over 2 from negative 4 to 0. And if I plug in, I'm going to pull that negative 5 halves out. When I plug in 0, 0 squared will be 0, but then I need to subtract from that the negative 4 plugged in. When you square a negative 4, that negative's going to go away and it'll just become positive 16, but it's being subtracted because we do the top bound minus the bottom bound. So this minus here and this minus here end up canceling out. This 0 goes away, and 62.4 times 5 halves times 16 is 2,496 pounds of fluid force. Okay? Now, just as an alternative, I want to show you that you could think of this problem without thinking in terms of a coordinate system. I would say that for a lot of problems that's tricky to do and it might lead you into having some problems, so I don't recommend it. But just to show you as an alternative for this problem only, you can imagine having your rectangular shape here, 5 by 4, and if you draw in a little slice, and you think of that depth y as being measured from the top down here, then your depth function could just be thought of as this y, just ignoring signs altogether and just thinking of it as that distance y. And then your length of this slice is again that constant 5. So your fluid force would be this w times the integral of h of y times the length of y dy, which would be 62.4 times the integral of this depth, which was our positive y, because we're ignoring our coordinate system here, and we're just thinking in terms of positive distances. Our length was 5. And how does this y need to range? Well, from the top down would be from 0 down to 4. So we want bounds from 0 to 4. So it's going to actually give you the exact same integral, 5y squared over 2, but everything's positive. So if you really don't like dealing with all of these negatives, you can sort of ignore your coordinate system and recreate this problem using positive bounds and positive depths. But for some of the trickier problems, I don't recommend doing it. Plus, it's nice to have one consistent way to do every problem, and that's usually how we're going to do it with our coordinate system like we did this first problem. So that's the way I'm going to continue to show you how to do these. Let's try another one. Find the fluid force on the indicated vertical side of a tank. Assume the tank is full of water. Assume the tank is semicircular in shape. So the tank here, I haven't drawn it out yet, but it's going to be a semicircle with a radius of 1. And to position this, I'm going to draw it again from that x-axis down. So this would be -1 and 1, and this would be -1 because it's going to be a semicircle of radius 1. And I'm going to position it coming down from that x-axis, and my slice would look something like this. So if I mark this side point here as just some generic x comma y, then this point right above it on the x-axis would have the same x value, but its y value would be 0. So this distance from the top down to that slice is our depth. That's what we're calling h of y. That's your depth function. And by using direction here, top minus bottom, that's going to be 0 minus y. So that's going to be a negative y for our function. Then we need our length of our slice. And the length of this slice, you'll notice that since I'm calling this x comma y, then this distance here is x, but so would this distance here if I think of x as being positive. So the full length going across would be 2x's. Now, unfortunately, for our fluid force problems, usually we're doing dy integrals because that's how we're measuring our depth in terms of that y coordinate. So I don't want x's here. I need to figure out what x is in terms of y. So that's where the shape comes into play, because this is a semicircle, which means it comes from the equation of a circle of radius 1, which is x squared plus y squared equals to 1. So if I solve this for x, subtract the y squared and take a square root, you get a plus or a minus, but I'm only going to take the positive square root because this x that I'm using down here in quadrant 4 is a positive x value. So we're going to use the positive square root so that we get a positive distance. So I'm going to replace this x right here with my square root. So this length function becomes 2 square root of 1 minus y squared. Now I'm ready to fill in my pieces. My fluid force F is going to be that weight density W times the integral of our depth function times our length. And in this problem, we're dealing with water again, so this is going to be a weight density of 62.4. Our depth function was negative y, and our length function was 2 square root of 1 minus y squared dy. And what are my bounds? Well, this y value ranges along this semicircle, so that y value is 0 at the top, and then it goes as low as this negative 1 down here at the bottom. So my bounds for y are negative 1 up to 0. You always want the lower bound on the bottom, the higher bound on the top. Now normally I would pull that 2 out and that negative out, but I'm actually going to leave it in. And I'm going to rewrite this as negative 2y times 1 minus y squared to the 1/2. And I'm leaving that negative 2y in there because that makes this perfect for pattern recognition. This is your outer function, f prime. This is your inner function, g. The derivative of 1 minus y squared is negative 2y, which is exactly what I have right here. So I have all the 3 pieces that I need for pattern recognition. So to integrate this, all I integrate is my outer power, and the integral of a 1/2 becomes a 3/2 times 2/3. What's inside stays inside. So I'm going to get 62.4 times 2/3. If I plug in 0, I'm going to get 1 minus 0 to the 3/2, which is just 1. If I plug in negative 1, negative 1 squared is positive 1, and 1 minus 1 will be 0. So the bottom bound actually gives me a 0. So we just get 62.4 times 2/3, which is 41.6, and our units here are pounds, pounds of fluid force. Okay, the next example, find the fluid force on the vertical rectangular plate submerged lengthwise in water if the plate is 2 feet wide and 5 feet long, and the top of the plate is 1 foot below the surface of the water. So the tricky part here is drawing this out and deciding what your coordinate system is going to look like. Now, if possible, I like to center my shape through the coordinate system. So I'm going to center my coordinate system through the middle of this rectangular plate. We have dimensions of 2 by 5, 2 feet wide, 5 feet long, and we also know that the top of the plate is 1 foot below the surface of the water. So if here's my axes, what I'm going to do is I'm going to represent the fact that this is 1 foot below the surface of the water. I'm going to go down 1 foot, and then I'm going to draw my plate, and I'm going to center it just like this. You don't have to draw it this way. You just want to pick a method and be consistent with it. Okay? So this is what my plate looks like in the water. It's vertical. It's 2 feet wide, so that's going to be this dimension, and 5 feet long, so that's going to be this dimension here, and 1 foot below the surface of the water. So I'm thinking of that x-axis as my water level. So let's draw in a slice going across. I'm going to label the corner point here as just some generic x comma y, and then this point up here would have the same x value, but the height would be 0. So the depth function using the direction here, this distance right here, top minus bottom would be 0 minus y. So we're going to get that negative y again for our depth. And then for our length, we want to know how wide this is. So it's this far out is our x, and this far out would also be that same x, but no matter where you draw your slice, notice that that's always a constant width of 5 because this is a nice rectangle. So every slice that I draw is going to have a length of 5 going across. So this is going to be 5. So my fluid force is that weight density times the integral of our depth times our width, dy. We're talking about water again, so this is 62.4. My height was negative y, my length was a constant of 5, and then the tricky part here are going to be my bounds. So what do we want this y value to range from? It needs to go from here to vary throughout this plate. We don't want to go above that or below that. So remember, we started out 1 foot below the surface of the water. So this height right here is actually -1 on my coordinate system. And since this is 2 feet wide, then that makes this -3 down here. So the y value that I'm using on this corner point ranges between -3 up to -1. So my bounds will be -3 to -1. So when I go to integrate that, I'm going to get 62.4 times the integral of -5y dy from -3 to -1. So that's 62.4 times -5y squared over 2 from -3 to -1. 62.4 times 5 over 2. And if I just plug in the -1 into that y squared, that becomes +1. Minus, if I plug in -3 and square it, that becomes +9. So this is 62.4 times 5 halves. I've lost my negative right here. -5 halves times -8. And so when you punch all that in, it does become positive because this negative from that depth and this negative from our bounds is going to cancel each other out. You should be getting a positive fluid force every time you do these problems. 1,248 pounds. All right, our next example. The figure illustrates the vertical side of a form for poured concrete that weighs 140.7 pounds per cubic foot. Determine the force on this part of the form. And I haven't actually drawn it yet, but this is what it's going to look like. It's going to have the shape of a triangle with a width of 5 here and 3 units going down. So that's my form, and I'm going to fill it in with concrete, which has a different weight density than what we've been dealing with. It's going to have a weight density of 140.7, so that's going to be our W. Now, in order to figure out the fluid force on this due to pouring in this concrete, we need to set up our coordinate system again, and how you do it is kind of up to you. What I am going to do is I'm going to center my y-axis over here and my x-axis here. And I'm going to have this form going down. So if I draw a slice, it would be over here, just like that. And this corner point I'm going to call just some random x comma y. And this point up above would have the same x value, but the y coordinate would be 0. So this depth right here, h of y, is going to be the top y value 0 minus the bottom y value. So this is going to be that -y again. Now, our length function is a little bit more complicated this time because this length function is the length going across here, which is not just our x, because we want to go as far over here as we can up to this point. Now, look at what we know here. This corner point, we actually know what the x is because it's always on this vertical line of x equals to 3. So this x coordinate on the edge on the right is 3. But this point over here is actually going to vary. It's going to have the same height y, but the x value will vary depending on where we are on this line that's coming down here. And this this horizontal distance going across would be this right endpoint minus this left endpoint. We're just subtracting the two x's, going right minus left. So this length would be 3 minus whatever that x is. Now, because we're doing our depth in terms of y, we want to do our lengths in terms of y as well. So we don't want that x in there. So we need to figure out a relationship between x and y, and that's going to be the relationship based on the equation of this line that's coming down. Now, what kind of equation would it have? Well, equations of lines are y equals mx plus b. This line goes right through the origin by the way that I centered my triangle. So the b here is 0. The slope, I go right 5, down 3. So my slope, when I do rise over run, it's actually going to be down 3, right 5. So my slope is going to be negative 3 over 5 times x plus 0. So that is the equation of that line. Now what I need to know is, what is this equation solved for in terms of x? So if I multiply by the reciprocal, this will be negative 5/3 y. And that is what I'm going to plug in right here. Now notice the double negative. You're going to get 3 minus this whole x, so minus my negative 5/3 y. The minus minus becomes plus, so this length function becomes 3 plus 5/3 y. So my fluid force formula is this W, this weight density, times the integral of our depth times our length, dy. For concrete, which is what we're pouring here, my W, my weight density, is 140.7. My depth was this negative y, and my length was this 3 plus 5/3 y. What kind of bounds do I want? How low and how high does this y value range? Well, this point down here is at negative 3, and the triangle stops at a height of 0. So I need my y to range between negative 3 up to 0. So there's my integral. Let's go ahead and pull out the negative and distribute this y across. So the negative comes out, the y goes across and gives me 3y plus 5/3 y squared dy. So the integral is going to be 3y squared over 2 plus 5y cubed over 9 from negative 3 to 0. When I plug in 0 here and here, that gives me both of those being 0, minus when I plug in negative 3, the negative goes away, 9 times 3 will give me 27 halves, plus negative 3 cubed is going to stay negative, so this will be negative 5 times 27 over 9. And this minus will cancel with this minus, so you will get a positive result here when you punch this into your calculator, and the end result is 1,055.25 pounds of fluid force. Okay, the next example has a cylindrical gasoline tank placed so that the axis of the cylinder is horizontal. Find the fluid force on a circular end of the tank if the tank is full, assuming the radius of the tank is 3 feet and the gasoline weighs 42 pounds per cubic foot. So that 42 is going to be our weight density. Now with circles, it's usually easiest to try and center your circle at the origin and measure your depth from the top or the water surface down. So that's what I'm going to try to do here. So we're talking about a cylindrical gasoline tank that's horizontal, so that you can imagine your tank's going to be this way. So the vertical face, if you took a cross section here, that vertical face would be staring out at us like this, and we're talking about the fluid force on that face, which is that circular shape. So I'm going to center that circle at the origin. This circle has a radius of 3 feet. So this is 3, this is -3, -3, and 3. The tank is full, and we have, since the tank is full, you can kind of imagine that the fluid level is all the way up to the brim there. Okay? So what we want to draw in next is our slice. So pick any place you want to draw your slice. Here's my end point, which is just some generic x comma y lying on that circle. Then this point right above it would have the same x, but its height, since we're at the top of our full tank, this is at a height of 3. Okay, we're measuring from the top of the tank down because it's full. So this depth is going to be this top y value minus this bottom y value. So this is going to be a depth function of 3 minus y. Okay, so as this tank gets more and more full, then you're going to have that water level rising up. Okay, now what about the length of this? Well, the length is going to be this distance here, which is the x value, plus this distance on this side, which is also x. So our length is going to be 2 x's. And we need to know what this is in terms of y, since we're going to do a dy integral. So what's the relationship between x and y? Well, it's going to be the equation of our circle, which is, in this case, by the way I set it up, a circle centered at the origin, so x squared plus y squared, equals to 9, since the radius is 3. So if I solve this for x, take the positive square root only, because we're using a positive distance for our x value here, then this becomes 2 times the square root of 9 minus y squared. So our fluid force is going to be our weight density for gasoline times the integral of our depth times our length, dy. So this is 42 times the integral of our depth, which is 3 minus y, times 2 times the square root of 9 minus y squared dy. And how does this y value vary? Since it's going around this circle, the lowest that it goes is -3, the highest that it goes is +3. So my bounds here would be -3 to 3. So let's go ahead and distribute here. We're going to get 42. Let me pull out my 2 as well. And if I distribute the 3, I'm going to get 3 times this square root minus y times this square root. Now this is one that you can certainly do on your function integrate. That's perfectly fine. I just want to show you a couple of options here for how to do this by hand. If I break up these two pieces here into 2 different integrals, then this first one will be 42 times 2 times that 3 pulled out times the square root of 9 minus y squared dy from -3 to 3 minus 42 times 2 times the integral from -3 to 3 of y times square root of 9 minus y squared dy. Now this second one over here is one like we've done before, where you have pattern recognition. The outer function is the square root, the inner function g is the 9 minus y squared, and the derivative of that wants to be a -2y. I have the y, I'm missing the -2, so I can counterbalance by a -1/2. So now I have the right g prime. So to integrate that, I integrate the square root, and the integral of a 1/2 power becomes a 3/2 times a 2/3, with what's inside staying the same. These 2's cancel out, the minuses cancel out, so this becomes just a plus 42 out front. Okay, now notice what's going to happen with the bounds on that second integral. When you plug in +3, 3 squared is 9, 9 minus 9 will be 0. When you plug in negative 3 quantity squared is positive 9. 9 minus 9 is 0. So both of these bounds make this 0, so this whole second integral ends up going to 0. It's actually an odd function over a symmetric interval, so the whole integral goes to 0, which is kind of odd, but that's what happens. So really the only part of this that's going to matter is this integral here. So if you look at this integral here, this is not something that we know the antiderivative of. We haven't actually learned how to find the antiderivative of the square root of 9 minus y squared. We can't use pattern recognition on it because we don't have that extra y out front. But we can figure this out geometrically, because if you think about what the square root of 9 minus y squared is, it's a semicircle, because we're going from negative 3 to 3 and we're only looking at the positive square root. So what would be the area of a semicircle with a radius of 3? Well, since this is just a semicircle, its area function would be 1/2 pi r squared. And if the radius is 3, then that's just going to be 1/2 pi times 3 squared, times this 42 times 2 times 3 that's already out front. And if you punch that into your calculator, you're going to get 3,562.57 pounds. And that would be the same answer you would get if you had just punched this integral in originally using that function integrate command. Alright, the last example is pretty similar to the one we just did, but we have a little bit of a change here. This time we have a porthole on a vertical side of a submarine submerged in seawater, is circular with diameter 1 foot. Find the fluid force on the porthole, assuming that the center is 15 feet below the surface. So the most important aspect of this is setting up your coordinate system first. And what I like to do is center my circle through the origin if I can. So here's my circle through the origin, and it says that the center is 15 feet below the surface. So if this is my center, then the surface of the water is actually way up here at a height of 15. Now the other option here, and this is totally up to you, is you could let your seawater level be 0 and then draw your circle down here at a depth of 15. So this would be negative 15, and that's perfectly okay to do as well. Alright, the reason that it's nicer sometimes to center your circle at the origin is because then the equation of that circle is just going to be x squared plus y squared, and you don't have any shifts involved because your center is just the origin. Now this particular circle has a diameter of 1 foot, which means its radius is 1/2 a foot, and a half squared would be 1/4. So the equation of this circle is just x squared plus y squared equals 1/4. This circle down here would be a little bit more complicated because it has a center at 0, negative 15. So its equation would be x squared plus y plus 15 quantity squared equals to 1/4 because of that shift in the center. So it's up to you which way you decide to do it. Obviously this is a little bit cleaner and easier to use than say this one over here. So that's why we tend to try and center our circles through the origin. But how you set up the problem is entirely up to you. Alright, so I'm going to stick with what I have over here on the left. And if I do that, then remember our water level is up here across the top. So when I draw my slice, and this is just some random point x comma y, then this point up here would be x comma 15 because we're up at a height of 15. So the depth of that slice, or this h of y function, is going to be this top y value, which is 15, minus this bottom y value, which is y. So here's our height function. Now we need to get our length function, and this x value is this horizontal distance going across. Whoops. So this is my x here, and I need the other side as well to be x. to give me a full length of 2x going across. So to figure out what that x is in terms of y, that's where this equation of the circle comes into play. And so we're going to need to solve this equation for x. So if I subtract my y and take a square root, we're going to use the positive square root. This is what we're going to get for our x. And now if we had done it the other way that I had drawn earlier over here, then that expression would be a little bit more complicated because the equation of our circle was a little bit more complicated. All right, we have our depth, we have our length, we're ready to find our force. So our force is going to be the weight density times the integral of our depth function times our length function. We're in seawater this time, so seawater has a weight density of 64 pounds per cubic foot. So we're going to use 64, and then our depth was this 15 minus y, and our length was this 2 times the square root of 1/4 minus y squared dy. And now what kind of bounds do we need? Well, we're looking at this y coordinate on the circle and how it's ranging. So we need to know how low and how high it goes. Since this was a circle with a radius of 1/2, then this is down here at -1/2 and this is up here at +1/2. So my bounds would be -1/2 to +1/2. So if I pull out my 2, this becomes 128. And this is very, very similar to the last integral that we attempted to solve here. So if I break this up and distribute my 15 across, I'm going to get 15 times the square root of 1/4 minus y squared minus y times the square root of 1/4 minus y squared dy. So breaking this up into two separate integrals, the 128 is being multiplied by both. So this first one will be 128 and a 15. I'm going to pull that 15 out with just this square root inside. The second integral only has the 128, not the 15, and inside is the y and the square root of 1/4 minus y squared dy. Now I won't go through all the work again because we just talked about it a minute ago, but this second integral can be solved using pattern recognition. You could put in a -2 and counterbalance with a -2. The minus and the minus cancel out, so this is going to be 64 again, and the integral of a square root is going to be 3/2 times 2/3. However, when you plug in your bounds, the 1/2 and the -1/2 both cause this to go to 0. So this is an odd function over a symmetric interval, so this whole second piece is going to contribute 0 to our answer. So it's only this first one that matters. And that, again, is that semicircle shape over -1/2 to 1/2. So we can't solve it algebraically because we don't know how to find the antiderivative of this, but if we just use a little bit of geometry, the area of my semicircle is 1/2 pi times the radius, which is 1/2, squared. And if you punch that into your calculator, you're going to end up with 753.98 pounds. And you can also do this using function integrate as well. All right, that concludes our lecture on force due to liquid pressure. Good luck.